Right, according to my various computers around the place, I am actually now online, and welcome to this talk on climate change and actuarial approaches to climate change. So let me just disappear for a second and put up the presentation. So what I'm going to do today is just talk a little bit about how I view climate change from mainly a modelling perspective. So looking at the data that's out there and the approaches that could be used for modelling climate change. And there is quite a lot of information out there and quite a lot for us to get our teeth into from a modelling point of view. So a lot of it is about how exactly we would go about that. Now, looking at climate change risk is a little bit different to looking at the way we normally consider risks in a risk management process. The usual approach to risk management is you first need to understand all of the context. So you need to understand the institution that you're looking at. You need to try and identify the stakeholders or stakeholder for which you're doing any of the risk management work. And then you need to understand the internal and external environments that both the institution and the stakeholders operate in. And once you've got all that information behind you, then you can start the traditional risk management process in terms of identifying the risks, assessing those risks, managing them, monitoring them, and modifying the process in a circular approach, kind of actuarial control cycle. Now, when we're looking at climate change risk, the process that we'd be considering would be slightly different, because what we're starting with is climate change risk. We're actually starting with defining the risk and trying to work out what exactly this risk is. And then we're trying to see, well, which institutions are affected by climate change risk. So which ones could we help? Then we need to understand their internal and external environment and how climate change risk might interplay with that environment. And then we assess the risk, manage it, monitor it, and modify it. So we're starting from a slightly different place. We're kind of almost assuming that one of these risks is already there and is always going to be a part of the discussion, which is not so much working for an institution, it's really trying to find out where our niche might be, where we might be able to add value. So this is something which I talk about quite a lot, and I did a post on this on LinkedIn recently. I talk about it in my lectures quite a bit, and it's about trying to understand what we mean by risk, because risk can mean different things to different people. Risk could just mean uncertainty over a range of outcomes, so it might just mean you don't know what's going to happen. It's more usually used to mean the possibility of bad outcomes. So uncertainty could mean good things happening and bad things happening. Normally when we're talking about risk, we're talking about just the bad outcomes. We're not usually concerned with upside risk, but it depends on the definition. But it might not just be the possibility of bad outcomes, so the fact that something could go wrong. It could also be the probability of bad outcomes, so actually putting a number on that. So when we're talking about risk in terms of, say, value at risk or standard deviations, that's what we're doing there. We're putting a number on it, and obviously standard deviations is more about uncertainty than around bad outcomes. But we can attach probabilities to things, and that's not always possible, but it is preferable, I think. When possible, we should try to attach numbers to the risks. If we can't attach numbers, it doesn't mean we should ignore the risks, absolutely not. But if we can quantify things, it does give us something better to hang an argument on. But it's not just, even then, the probability of bad outcomes. It could also be the consequences of the bad outcomes. And this is quite important. It's something which the Intergovernmental Panel on Climate Change talks about as well. It's not just something going wrong and not necessarily having any additional effect. It's the consequences which are important as well. And those can also be regarded as the risk. So if we look at sea levels, rising sea levels as an example. So if we look at it in terms of uncertainty over a range of outcomes, we could say, well, sea levels may rise or they may fall. If we talk about the possibility of just bad outcomes, it's just sea levels may rise. We're not interested in the chance of them falling, it's just if they go up. The probability of bad outcomes, the likelihood of a particular level of sea rise, or the probability that the sea level will rise above a certain limit. or the consequences of bad outcomes. So here we're looking at things like the insurance or financial market loss or even loss of life from sea level rises. So if the sea level rises on some deserted island and there's no consequence apart from the fact the island that nobody lives on gets flooded more, that's not necessarily a risk in some people's eyes. If it's London flooding, then that's more of a risk. So it's and the consequences is quite important from a climate change point of view, because what we're talking about is not just some chance of the weather changing or the climate changing, but we're looking at the implications of that for the way of life, for financial markets, for a whole range of factors. So the IPCC, the Intergovernmental Panel on Climate Change, this is what they think of risk. And it is this extremely long document talking about what their view of the concept of risk is. And it is actually a very good document. It outlines all of the important factors around what risk does and doesn't mean. And the reason that they did this was because they could see with the previous work there was a lack of consistency in what different authors were meaning when they were talking about risk. So this piece of work was put together to try to ensure consistency in the use of the concept of risk, both across all the working groups, because the work they do is carried out by a large number of authors, but also over time as well. And their core definition of risk is the potential for adverse consequences. So it refers only to negative consequences. And they explicitly say that the potential for positive outcomes from climate change should use other terminology. So they shouldn't refer to it as upside risk. They should refer to it as something like opportunity or something else. They also say that it shouldn't describe outcomes within physical systems only. So for example, flood risk. If you're just describing changes in the frequency and intensity of flood events with no other consequences, that's not something which they would consider under their definition of risk. But if it's linked explicitly to the consequences for human or ecological systems, then it becomes a risk. And they also apply risk to both impacts of and responses to climate change. Now, one of the interesting things that they also do is they shy away from probabilities, but they do have some broad guidelines around statements such as more likely, very likely, neither likely or unlikely, and so on, to give guidance on those broad kind of probability buckets that authors should be using when they're writing about climate risk. So it is a very good document and definitely worth a read. So when I think about risk and climate change, whenever you're looking at risks and the way of classifying risks, different people have different ways of doing it, and there isn't a right or a wrong way, and many of the divisions are quite arbitrary. One of the divisions I think that can be quite helpful is dividing the risks into direct risks and indirect risks. So the direct risks might be things like increased air and sea temperature, which could lead to crop failures, lower fish stocks, increased need for cooling in hot countries. Increased sea levels is a direct risk, which could lead to loss of life, land, buildings and infrastructure due to flooding. Increased or reduced rainfall, this could lead to crop failure, loss of farmland, losses due to flooding, and the increased frequency or severity of extreme weather events, again, loss of life, land, buildings or infrastructure due to extreme events. Now these are very direct consequences that you might have from climate change. So the climate changes, you have an event, it impacts directly. But these aren't the only implications of climate change, and they're not the only ones that we should be interested in potentially dealing with. So you have a number of indirect risks which are more or less easy to quantify, and I'll talk about these in a bit more detail later on. So you have things like the impact on company profits or share prices, and there's many potential mechanisms for this. The fact that markets and financial services and companies and investments may be affected by climate change is a very important area where we could contribute in terms of modelling, but it's certainly not one which is straightforward. There's also clearly the impact on the price of other assets, such as bonds, but also clearly real estate. You know, if you have real estate in an area which is prone to flooding, then that is going to be adversely affected by climate change. So that is an indirect risk, the price of the asset, rather than the fact that it may flood. But it is something which can be modelled. Then you get things like taxation levels. The financial impacts of climate change mean that governments may need to make some difficult choices. What is going to happen to taxation around the world because of the costs associated with climate change? Also legal costs. If some parties are found to be at fault through their actions or inactions, there could be additional costs there. Reputational losses as well. We've already seen this, that climate unfriendly companies may lose customers, may lose profits because just of what they do, and that could continue. So there's a number of ways in which climate change can indirectly affect people, can affect economies, and this does need to be modelled and does need to be considered. So in terms of modelling climate change, there's been a lot of work done in this area. Most of it though is scenario based, so it's deterministic, so it's looking at potential pathways for how the climate may change, or how some of the contributors to climate change may develop over time. And this is useful, and this is what was distilled into the IPCC's latest report, a core number of 4 scenarios, which we'll look at a bit later. But I think there's enough information out there that you can attempt a stochastic approach for this. Now, I'm not going to present a stochastic approach. What I'm going to do is ask some questions about how it could be done and the sort of things which might need to be considered and the way we might need to think about them. But I think before we look at how we might stochastically model climate change, I think it is worth understanding the drivers of climate change. Now, one of the things I meant to say at the start was that I'm covering a lot of different areas in this presentation. Some of it is going to be going over old ground that a lot of people will know very well already, and if that's you, I apologise. Other bits later on are going to be much more technical and might not be as much interest to the generalists. Again, for those I apologise. Hopefully everybody will find something in here which is useful, but for those that are not completely familiar with the history of climate change and what causes it, here's a primer. So this is just looking at the history of the Earth's temperature. Just a question saying, can I get a list of important papers on the topic? I'm not an expert on climate change, but I think a lot of the papers which I referred to in this presentation, which you'll be able to see if you play back this video, and I'll make the presentation available later. A lot of the references here are useful, and looking at the IPCC reports is a pretty good starting point. So this is looking at the history of the Earth's temperature. We can see that it started off around 10 degrees hotter than it is now, up to almost 15 degrees hotter than the present day, which is extremely hot. I mean, it's almost as hot as Dubai in summer, but not quite. Then the temperature gradually fell over time, and an important thing to note on the scale here is it's not a constant scale on the horizontal axis. So the first block is million years before the present, the second block is thousands of years before the present, and the final block is in years. So in the first 60 million years, we saw the temperature broadly gradually falling. And then we got these spikes of temperature rises and then falls, rises and then falls to about 20,000 years before the present. Then we came out of our last ice age about 12,000 years ago, relative temperature stability, and then we started burning stuff and the temperature started to rise. Now, the fan chart at the end is just showing some scenarios from different modelers, and you can see from some of those which assume no changes in behaviour, by the year 2300 we'll be up to the same kind of temperatures that we had before single-celled organisms have really got a grip on the planet. So the potential for things to go wrong is quite extreme. Now, one of the main culprits for global warming is CO2 density. And you can see that over the very long term, carbon dioxide density has varied considerably. And you saw the temperature has varied considerably as well. The mechanism of the interaction between carbon dioxide and the Earth's temperature, though, wasn't necessarily the same as it is now. So in the past, what we might have seen would be some external factor leading to the Earth warming up, which made it more habitable, which meant that you had more life on Earth being born, which created more carbon dioxide, and this happened in a cyclical fashion, and happened over very long time horizons. So carbon dioxide could have been the consequence rather than the cause of previous cases of global warming. Now, that's not the case today, and there's some very good evidence to suggest why that isn't the case today, that it is carbon dioxide which is causing global warming. But it is an important point to note that it's not just a one-way street in terms of causality. You can have greenhouse gases causing warming, but you could also have warming causing greenhouse gases, which is a problem, because if you have greenhouse gases, you're creating the greenhouse gases and causing the warming, and that then creates other forms of greenhouse gases. You're creating quite a dangerous environment. So the panel on the right, this looks at again a slightly different time frame zoned approach. So first millions of years, thousands of years, and then the present day. And you can see that coming out of the Ice Age, we end up with very stable levels of carbon dioxide. And then under this range of scenarios, which we'll talk about, the IPCC ones, we can see that there are a number of different potential scenarios that are considered. One of which leads to carbon dioxide levels which are as high as they have ever been. And you can see if you look at temperature change and CO2, carbon dioxide starts to go up, the temperature's gone up, there's quite a close apparent correlation between these two. But carbon dioxide is not the only culprit in terms of greenhouse gases. It's probably about 60% of the impact of global warming comes from carbon dioxide in terms of the greenhouse gases. There are other greenhouse gases in lower concentrations, but potentially much more potent. For example, methane. If you look at this chart here on the right, showing what methane levels have been like over the last couple of thousand years, that is quite an extreme change. You can see that there's quite a lot of variability between 1000 AD and 1800, but since 1800, since the Earth has started to warm a little bit, it's gone absolutely ballistic. It's increased hugely. Now this is interesting mainly because of the causes. If you look at the causes of atmospheric methane, by far the biggest cause is wetlands and tundra, over 60% of the total. And incidentally, methane is several hundred times as potent as a greenhouse gas as carbon dioxide, so it is quite important. Now, because it's coming from wetlands and tundra, that's not stuff that we're creating. That is stuff which is being given off because the climate is warming. So this is what I was saying before about a feedback effect, that the increased levels of CO2, which are mainly man-made, another chart on that later on, that's causing global warming. That's causing the tundra to warm up, frozen tundra to warm up, which is causing methane to be released into the atmosphere, which will cause further global warming. So this is quite important from a modelling point of view, because we need to think about how we should model these different greenhouse gases together, how they interact together. They don't necessarily change independently. So there's quite it poses some interesting modelling questions when we look at that aspect. The third greenhouse gas is nitrous oxide. So nitrous oxide, which people might also know as laughing gas, might also know as what you inject into car engines in drag races to make them go faster, and also what you inject into canned whipped cream to make it expand and come out onto fluffy toppings on desserts. Nitrous oxide is also a greenhouse gas. And again, the mechanism of nitrous oxide and how it comes about is quite interesting. A lot of it comes from agriculture. So nitrogen fertilizers, which are put out to try to help crops grow. Now, what that means is that even if we are not burning as much, if the population is growing and we need more crops, then potentially we're going to be using more fertilizer. Nitrous oxide is still going to be a problem. And also a lot of it comes from the soil, from microbes, which are more active when the temperature is higher. So global warming, again, can cause more nitrous oxide to be released. It's not just using the fertilizer, it's the temperature of the ground on which the fertilizer is put, and those natural mechanisms causing high levels of release of nitrous oxide into the atmosphere. It also means there's an interesting potential quandary, because if you look back at methane, one of the other main sources of methane is animals. So I'm sure many people know that the carbon footprint of, or the greenhouse gas footprint of Australia is probably to a very large extent from the amount of livestock they have there and the methane that the livestock produces. So what you could do is say, well, if people became vegetarian, you wouldn't have so much methane. No, but you might have more vegetables, which means more fertilizers, which means you might have more nitrous oxide. So it is quite a, with a lot of people, there's going to be greenhouse gases produced. So this is what greenhouse gas concentrations over the last 2,000 years look like. And it does kind of look like when the Industrial Revolution came along, things started getting a bit out of control. What's quite interesting is the pattern of these, so the shape of them as well. And this is another interesting modelling aspect, that although you've got more or less exponential growth, it's not uniformly exponential. There's some little kinks in the line there. Now, what does that mean for the way in which we should be modelling these processes? That's definitely something which we should consider, that you might want to have a slightly more involved model for the development of these things over time into the future to capture some of these features. And I shall talk about that a little later. Now, one thing which some people talk about is the possibility that greenhouse gases aren't the culprit, that global warming is more about the effect of the sun on climate change. They talk about things like sunspots and even things like Milankovitch cycles. Now, Milankovitch cycles are very interesting and probably do have some kind of impact. The theory behind Milankovitch cycles is that whilst the Earth has a pretty stable orbit around the Sun, it is going to be distorted by the effect of other planets. So if you get alignment on other planets, those will, to a very small extent, pull the Earth away from its orbit, or push it a little closer into the Sun, or make some other changes. And various alignments can have different effects, and all of these could have an effect on the Earth's climate. And there is some evidence that this might be the case, but over very long time horizons, and certainly not to the extent that we've seen the level of warming that we have over the last century and a half. Sunspots as well is quite interesting. There does appear to be some link between sunspots and the temperature on Earth. So the more sunspots there are, the higher the temperature on Earth, or the more active the sun is, the more radiation the sun gives out. And the sun, in terms of sunspots, operates on about an 11-year cycle. So you get these 11-year cycles which peak in a maximum number of sunspots and then it dies away. And there was a period in the 17th century where there were virtually no sunspots and the sun was much less active. We had something called the Maunder minimum, which meant that the River Thames was regularly used as a skating rink because the temperature was so much lower. So sunspots and solar activity could have an impact on the climate. But what we're seeing is the level of solar activity has actually been decreasing over the last few decades. So it certainly doesn't explain the fact that the Earth is getting warmer, that we're seeing higher temperature on Earth. And a really good graphic which shows that greenhouse gases are the more likely culprit is this one here. So these two charts on the left-hand side, these look at temperature anomalies in the lower stratosphere and in the lower troposphere and on the surface. So the troposphere is a bit of the atmosphere closest to the Earth. Above that, you've got the stratosphere. And what you can see is that since 1950, the average temperature in the stratosphere has been declining. There's been a few peaks from volcanic activity, but overall the temperature in the stratosphere has been declining. However, the temperature on the surface has been increasing. So what this suggests is that solar activity is doing less of the work, but greenhouse gases are doing more of the work. It's a bit like if you're trying to boil rice and you've got the pot boiling, so you turn the gas down a bit and it stops boiling, but you put the pan lid on, and that causes it to start boiling again. The input from below is less, the lid on the top is still keeping the temperature up. And the rate at which we're seeing greenhouse gases go up at the moment is a bit like pushing the lid on, clamping it down, forgetting about it, and seeing all water evaporate and the rice burn and stick to the bottom of the pan. It's that kind of level of problem. So, and that's a very brief run through some of the numbers behind climate change and some of the causes of climate change. How could we use this information in an actuarial modelling approach? There is a challenge that has been made to actuaries in the past, that what we often do is essentially driving using the rear view mirror. So we look at what's happened in the past, and then we just use that to blindly project what's going to happen in the future, which for climate change is not necessarily appropriate. And well, for most things it's not appropriate. I mean, it is, even in financial modelling, you will use some sort of external estimate of what the future might look like, hopefully from the market or something similar, and you use history for things where historical data is more useful, such as volatilities or correlations or something similar. So the relationships between variables, the history is quite important. Looking forward, you use something else, you use the market. Now, you can't really use the market for modelling climate change, modelling emissions. What you need is some sort of expert opinion on some of these values. And for this, it is quite useful looking at what the IPCC has done, because it's used a lot of academic rigour. What is important to try to avoid is projections which are newsworthy. Things are newsworthy usually because they're extreme rather than because they're balanced. So things which predict the extinction of the human race in the next 50 years due to climate change, or others which predict that climate change is going to create a new nirvana and vineyards in Scotland. These types of things are not particularly helpful from a modelling point of view. Rigorous, peer-reviewed academic evidence is much more useful. And if you can have that curated somehow, put together, which is what the IPCC does to an extent, that can be a very useful approach. So one of the things that the IPCC does in its fifth assessment report was to come up with things called the representative concentration pathways. And these described 4 different 21st century pathways of greenhouse gas emissions and atmospheric concentrations, air pollutant emissions, and land use. And it developed these using what he called integrated assessment models, which it would then put out to a wide range of different simulations to project consequences for the climate system. And then also to say, what should we do about this? Now, they narrowed down all of the projections that were available to them to 4 scenarios. RCPs 2.6, 4.5, 6.0 and 8.5. So 2.6 was the stringent mitigation scenario. 8.5 was the very high greenhouse gas emission scenario, and 4.5 and 6 were in the middle. So 2.6 is representative of a scenario that aimed to keep global warming below 2% above pre-industrial temperatures, which generally implied substantial net negative emissions by the year 2100, which is quite aggressive. So AR5 is useful for a number of reasons. First is it's got a lot of detailed historical information, a lot of information on how land and ocean surface temperatures have changed over time, how sea ice has changed, how the sea level has changed. It's also, as well as these climate-wide numbers, it's also got very granular information on how temperatures have changed over very small areas across the whole globe, which is very useful, and also how rainfall has changed across the whole globe. Because, as you know, it's not necessarily an issue that there's overall more or less rain; it's where it falls and where it doesn't fall. So you could see climate change causing floods in some parts of the world and drought in others. Also, you can see this chart here, which is on the bottom right, which I think is very interesting and helpful, which shows the global anthropogenic CO2 emissions. So it shows how much of CO2 emissions are down to man, and especially those that are down to fossil fuels, cement and flaring. So just flaring off gas from oil fields. And you can see it's big numbers, it's most of it. What's also quite interesting is, even for the historical numbers, it does include some confidence intervals, looking at what the range of views, what the range of potential impacts might be for different things. So for observed warming, pretty confident that it's anthropogenic. Greenhouse gas contribution, pretty confident in what that is. And other things like natural forcings, so solar power, solar energy, for example, energy from the sun to the earth, less convinced on that, but pretty convinced from all the evidence that combined anthropogenic forcings, the combined effect of what we're doing, is positive on the temperature change, or has been since 1951 to 2010. So this is useful because it gives us a lot of historical information which we can mine to build our model. What's also very useful is it includes a lot of granular forward-looking assessments. So under the various different scenarios, it doesn't just say what the overall temperature change might be, but what that temperature might be across the globe in different parts of the world, which is really useful. So you can see which parts of the world might be more or less adversely affected by climate change. And this kind of expert opinion is really vital, because you can't get it from looking at prices and trying to infer what the market is telling you. And similarly for precipitation as well. So we have similar views on what the change in rainfall might be across the globe, where it might fall more or where it might fall less over the next 100 years. So this forward-looking stuff is really important when we're trying to build a model, because then we can take what the experts have done and feed it into our final assessments. Something else which is useful and which is out there is impacts, the uncertainty estimates of the impact of greenhouse gases. So people are broadly agreed that greenhouse gases are the main cause of global warming, but the impact of greenhouse gases is something which is less well agreed upon. I mean, it's pretty well agreed upon, but there is a range. And different approaches come up with different numbers. So what the charts on the left do is they say, well, if the global CO2 levels doubled from pre-industrial times, what would the expected change in the global temperature be? And the estimate is around 3 degrees, but there's a range around that, there's a confidence interval around that, which is useful because it means that when we're projecting what the greenhouse gas levels might be, we can then use those to model what the impact on temperature might be and factor in some uncertainty around those results. So these charts here are taken from a paper relating to to AR5, the representative concentration pathways, and it looks at what the projected concentrations of those 3 greenhouse gases are from 2000 to 2100 under the different scenarios, which is quite interesting. What's more interesting to me is the grey shaded areas there. Now those shaded areas, what they give is the 95 and 98% confidence intervals. And what that means is that with this information here, we can plot our forward expectation of CO2, CH4 and N2O, and we can also plot the variability in that over time, so the standard deviation of that change in these greenhouse gases over time. And that's most of what you need for a forward-looking model, is your central assumption and the variability around it. And then if you want to look at what the relationship between these gases will be, well then you need to build some sort of correlations in, which you can get from historical data. So if I was going to build a stochastic climate change model, this is the sort of approach that I would use. I'll start with modelling climate change variables, mainly greenhouse gases, maybe solar forcing, but I don't think this is important, but mainly the greenhouse gases. And I would use those to give me an indication of what the global temperature would be. And then I would take that global temperature and see what the AR5 projection said, the regional temperatures, sea levels, extreme events and so on would be on a more local basis given a particular global temperature. So I'd have almost stochastic uncertainty at the start in the greenhouse gas variables, a little bit of that flowing through into global temperature, and then the last little bit I'd make that deterministic, and that would allow me to have some sort of ultimately stochastic view on whatever particular item I was most interested in at the end. So modelling the development of greenhouse gases. I've already said you can use the percentiles that we've been given to derive the path of trend and volatility. Now, what kind of model might we use to project these gases going forward? Log normal random walk. I mean, we could just use a random walk. The problem with a random walk is that it would allow some of these concentrations to theoretically go negative, which is theoretically a bit of a problem. So you might want to have a log normal random walk to prevent the possibility of negative greenhouse gas concentrations. Of course, log normal random walk allows them to go to infinity, and there's a limited amount of carbon in the world, so that's also improbable. But I don't think we'd reach that in any of the scenarios. So log normal random walk. What would also be interesting though is how do you link these series together? Would you allow them to be correlated, or would you allow them to be co-integrated? And it's quite an important decision to make. It's one which I've looked at before in terms of mortality modelling, and also investment modelling as well. So if you've got two things which are correlated, the changes that you see, there is some link between those changes, but there's nothing which means that two variables which start off in the same kind of place would ultimately end up in the same kind of place. Just because things are correlated, they can still quite easily end up in very different positions. So correlation means that each individual change might be quite similar, but the endpoint could be quite a long way away. And clearly that doesn't really matter so much if you're looking in terms of returns for investments. If you're looking at mortality rates, say looking at modelling male and female mortality rates, it's quite unlikely that they'll diverge massively, never to converge again. So for something like that, you might want to look at co-integration. And co-integration means that the changes aren't so much correlated, but the further away they get pulled back towards each other. So there's a mechanism which keeps the different time series within a particular range of each other. So if you're looking at, say, CO2 and methane, you might expect there to be a degree of co-integration there. Because increasing CO2 concentrations, which would lead to higher temperatures, would lead to more methane. For nitrous oxide, potentially you might have some co-integration there, which could come from the fact that CO2 concentrations are linked to population, and so is the use of fertiliser, but the link is more tenuous. Unfortunately, it's not the sort of decision you just have to take a view on. You can actually look at the data and perform some tests to see whether things are correlated or co-integrated. And that's certainly something which I would want to do. Also, random walk or trend change. When I saw this temperature chart here, the temperature anomaly, it reminded me of some work I did a while back on the change in the parameters for a particular mortality model. It had always been modelled as a random walk. And I said, well, I don't really think it looks like a random walk. It looks more like everything follows a trend. You get some noise around the trend, and then the trend changes. And that approach works quite well for the fitting of mortality. It seems to look reasonable for the changes in temperature, and it could potentially be something which could be used to model greenhouse gas concentrations as well, because if you look at changes in regulations, for example, those could have a significant, fairly short-term effect on the path of CO2 emissions. So rather than just having a random walk, having something where the trend could change periodically is not an entirely unreasonable idea. So having that, so looking at the past data and seeing whether there is that sort of pattern, that's something which could be quite interesting. And integrating radiative forcing, the solar forcing, the power of the sun, you could do, and I don't think it would hurt. It might be useful if you saw any slowing down of the change in the temperature despite carbon dioxide emissions continuing to rise, because if you had reduced solar forcing offsetting some of the impact of carbon dioxide, that might not necessarily be the case in the future. So it could be something to make sure that scenarios were not unnecessarily optimistic, but most of the evidence seems to suggest the effect is either weak or at least very difficult to capture in models. So then modelling temperature change. The first question I'd have, and as one I don't know the answer to, is the relationship between greenhouse gases and temperature changes linear? So is it the case that if you would expect a 3% increase in the temperature with a doubling of CO2, you'd expect a 6% change if it's quadrupled? Or would you expect more, or would you expect less? I have no idea. I'm sure people have looked into this, but it would be interesting to try to see what that relationship should be. Also, would it be a one-for-one relationship, or would there be some sort of autoregressive or moving average component? So if you reached a particular level of CO2 and then it just stopped, I wouldn't have thought the temperature increase would also just stop. It will carry on for a while and then stabilise. So there would be potentially some lag and potentially some sort of autoregressive process carrying on. So it would be interesting to see whether there's that sort of relationship which could be shown from historical data, or could be certainly modelled going forward. But then what I'd do is I would set up just a formulaic relationship without an error term at the end, but instead include parameter uncertainty. So I'd say set the temperature equal to this polynomial here, so constant plus a couple of factors times whatever carbon dioxide is, a couple of factors times methane, a couple of factors times nitrous oxide, including the squares as well. But for each scenario, I would pick the values of the alphas and the betas randomly from a distribution which reflects their uncertainty, and just plug those in for the whole of that scenario. So if from one scenario we decided that the effect of doubling carbon dioxide concentration was for the temperature to increase by a factor of 1.5, for all of those carbon dioxide concentrations, the temperature being chucked out of the model at the end will be based on a 1.5 multiple for doubling, and no volatility around that. And then when we've done that, and we've got all these temperature change values for the system as a whole, then we can use that to infer from those RCP, those representative concentration pathways, what happens on the thing that we're most concerned with. And that thing might be temperature in a particular region, in a particular city, in a particular area. Because what we can do then is we can say, well, run the model, and then we can see what the likelihood of the maximum summer temperature in a particular city rising being greater than 3% above its current level in 20 years' time. And use that to help work out what sort of power needs there might be, what sort of infrastructure changes there might need to be in that particular area. So that's the approach that I would use. I just wanted also to touch on climate change and investments, because I think it's a fairly important area. It's something which a lot of people are looking at, and it's something where I think some better modelling could be done. Because again, a lot of the stuff I've seen is on the scenario testing side, and I think also it's important to recognise some of the caveats, so some of the limitations that this sort of analysis might have. Now, there's several different approaches, or several different things we might want to consider here when we look at climate change investments. The first is a kind of macro view. What might climate change do to particular asset classes? What might it do to equities as a whole? Then the second part is what stock-specific factors might be at work. So if climate change is worse than expected, what securities might perform worse or might perform better? And as I say, this scenario analysis has been used a lot. I think a stochastic approach could work as well. I think for both of these, there's two ways of doing it. There's a top-down approach and a bottom-up approach. So the top-down approach, you could look at what real returns you might expect versus changes in GDP, changes in population, and so on, drawing that information from AR5 or similar reports. So taking some macro variables coming out of the modelling, and then just looking at the relationship between those macro variables and individual asset classes. Because the time horizons that we're looking over, companies will change, and will change a lot. I remember when I first started looking at the I think it was Benjamin Graham book on security analysis. A lot of the analysis that he carries out is on snuff manufacturers being a considerable part of the index at the time. I don't think there's many snuff manufacturers on the New York Stock Exchange anymore. Even for individual companies, I mean, if you look at a company like Shell, for example, I mean, as you probably know, Shell started as a company which sold shells. It imported shells from, I believe, Crimea and Black Sea, and that was its business. Then it discovered there was some kerosene there as well that it could sell for lamps, and that became a slightly more dominant part of its business. So what companies do over time can change a lot. More recently, Amazon used to be a bookseller, online bookseller, now sells groceries. So companies can change a lot in fairly short periods of time. So looking at what the impact might be, I think looking at these longer time horizons and these bigger factors, things like how GDP growth affects the market generally is not an unreasonable approach. It also means there needs to be a little bit of caution used when we're looking at a bottom-up type approach. So looking at the sources of return of each security, assessing the sensitivity of that return stream to climate change, and inferring the change in the value of the security. That can be done, but it's important to recognise that those streams may not necessarily change. And also trying to look at the correlation of these changes with other investments correlations. They're more predictable than investment returns, but they're still not completely predictable. So there just needs to be some caution there. Some of the caveats, though. The first caveat I'd have is around trying to make money out of a, say, climate-aware strategy. The market is certainly not always right, but trying to work out how the market is wrong is really hard. That's why it's difficult to pick active managers, because if active management was easy, then more active managers would be right more of the time, and they're not necessarily. A lot of active managers do struggle. So trying to work out why the market is wrong is difficult. Now, if we think the market is right, that must mean as a starting point that in terms of its assessment of which stocks will on average benefit and lose from predicted changes in the climate is a reasonably good starting point. So focusing on climate-aware stocks might not maximise returns. And I know there is a focus on moving to climate-aware stocks. There is actually a risk that if too many institutional investors were to focus on climate-aware stocks, then that might push those stocks to be overpriced and might mean that some of the less environmentally attractive stocks were underpriced. Having said that, it could also be a positive force in terms of decarbonising the economy, because if capital is allocated more to more climate-aware stocks and away from less climate-aware stocks, what has essentially happened is the cost of capital for more climate-aware companies has gone down, the cost of capital for less climate-aware companies has gone up. So it becomes less economically efficient to be environmentally unfriendly. So it could be used as a force for good, recognising that there might be some economic inefficiencies in directing capital in that way. And of course, the thing to be aware of in this sort of scenario is greenwashing, trying to avoid being hoodwinked by companies that try to make themselves look more environmentally aware than they are. Now this slide here, this is just one which I was just thinking of as I was finishing off the presentation. And it was just another way of thinking about climate change risk when we're looking at, say, a portfolio of securities. And this is some work which I did a while ago, which was, we started doing it when we were looking at sponsor covenant risk. What we were trying to do was to say, you've got risk and return in a pension scheme, but also there's some risk of the sponsoring employer not being around to make good their promises. And the sponsoring employer might be subject to particular economic stresses. So what you could do is you could have this as an additional risk metric. And it's based around conditional value at risk. So conditional value at risk says, if I wanted to say the 90% 10-day CVAR for a company, I'd look at the returns over the last, over as many 10-day periods I could get. I'd pick the 10% of the worst cases, so the worst 10% of cases, and I average those. And that tells me that if things go wrong for this company, then on average, this is how badly they go wrong. So that's the C-bar. Look at this cross-return C-bar. It's quite similar. What you'd do instead is you'd say, let's look at, say, the worst 10% of climate change outcomes in terms of temperature rises. Now, looking at those scenarios, those 10% worst case scenarios, let's look at what our portfolio would have done in those scenarios. And let's look at the average return of the portfolio for that worst 10% of scenarios. And that tells me what my expected portfolio return would be if we get the worst 10% of climate change outcomes. So it's another statistic which can be used to compare portfolios. You could look at the expected return, the C-VAR, which is a measure of risk. And then you could look at an environmental cross-return C-VAR to say, well, how environmentally exposed is this portfolio? Now, that was everything I was planning on saying. I've been looking at some of the questions coming through, and I have to say, many of them I just don't know the answer to. The Nordhaus DICE model, it rings a bell. I'm not familiar enough to make any comment on it. Machine learning and climate change. What could be done in terms of machine learning and climate change? I think one thing that could be done with machine learning is to take the very large number of papers that there are and to draw out the key conclusions for comparison across papers, because there's a lot of research being done, an awful lot, and you can read it and try to aggregate stuff, but machine learning would be much better at pulling that research in. One of the challenges with using machine learning on the climate information that we have is that the number of data points is still not huge. The time horizon that you've got good data for in terms of consistent from a particular part of the world is going to be, what, since the 1950s onwards, unless you're looking at ice cores. So you've got 70 observations. And if you've got too many series of 70 observations, you end up with more series than observations, and any inferences from that could be quite tricky. You could maybe use machine learning to try to put these series together. But machine learning, I think, works best when you've got an awful lot of data and you want to do something with it. And whilst we're doing a lot of research, or a lot of research is being done, shall I say, the number of data points is still not huge. I don't think. I could be wrong, but I don't think it's huge. So in terms of top-down and bottom-up for modelling, what do I recommend for investment consulting businesses? I think it depends what you want, what type of business you want to do. I mean, most of the stuff that I would suggest would be on a top-down basis if I was doing asset allocation modelling. If I was trying to work out what the asset allocation should be based on climate change as a risk, then I'd be looking at top-down. If I was trying to help clients build more environmentally friendly portfolios, then a bottom-up basis might be one that I'd choose. It's going to require a lot more data to do, and there are caveats around the company you invest in now might have a very different profile in 5 years' time than it currently does. But I think it depends on the type of work that you want to do for your client, whether you want to build them a portfolio of asset classes or you want to give them more advice on how they should build a particular asset class. I suspect that the second of those is becoming more important, and there is a growing market for that type of business. Right, I think we are almost out of time, so if there are no more questions coming up, I will, I think, end it there. Thank you very much for joining. I hope you found that useful. Do feel free to contact me on LinkedIn if you have any further questions or comments at all. Yeah, and let me know if you'd like to do another one of these talks on another topic of interest. Thank you very much.